YouTube. So lecture 2 of number theory. Any questions about any of the homeworks?
Yes, I have a question. So about the some of the problems, like finding all the divisor of a certain large number, or
Yes.
the one question about finding the tematic representation of some larger number. Was there a method that you showed in class in which we could find those, or we can just use any method that we want?
Well, so if you have to solve a problem, you can use any method whatsoever, right? The idea is to solve the problem, and however you solve it, if it works, and you have the right answer. So the object is to answer the question. And if you use a method you learned in class, that's fine. And if you use a method that you learned somewhere else or discovered for yourself, that's also fine. So for example, in section 1.1, exercise 6, we have the number 526. And we want to find the M-adic representation for different values of M. 2, 3, 7, 9. So let's look at the M equal 2, or the binary representation. So the algorithm, or one algorithm, is always to look for the largest power of M that's less than or equal to the number. So if you look at the powers of 2, 1, 2, 4, 8, 16, 32, 64, 128, 256, 512, 10, 24, the number 526 is between these two powers of 2. So the largest power of 2, no bigger than 526, is 512. So you can take 526 and say, well, this is going to be equal to 512 plus something. And what is the something? Well, it's 526 minus 512. Let's just call it X for the moment. So this number X is 526 minus 512. That's 14. So how do you write 14 as a sum of powers of 2? Well, 14 is between 8 and 16. This is going to be equal to 8 plus something. Well, that's easy. That's 8 plus 6. And 6, I can just do that in our heads, 4 plus 2. So if you put this all together, 526 is 512 plus X. X is 8 plus 6. 6 is 4 plus 2. So this is 2 to the power 9 plus 2 cubed plus 2 squared plus 2 to the first power. So this is the two-adic representation of 526. I'm writing 526 as a sum of powers of 2. Okay. Any questions about this? This is a basic exercise in elementary number theory. This is the two-adic representation. So this is the two-adic.
Okay, I just wanted to make sure that I didn't miss anything
Right.
in the
Well,
previous
let
lecture.
me do one more. Let me work that. Look at M equal 3. Let's find the three-adic representation. So you have to know what are the powers of 3. 1, 3, 9, 27, 81, 243, 729. 526 is between 243 and 729. So 526, we would write that as 243 plus something. Let me just call it y. And this number y, that's 526 minus 243. If we subtract, I think we get 283. 283 is also between these two powers of 2. So I'm going to write this as 243 plus, well, that's easy, plus 40. So what I have so far is that 526 is 243 plus 243 plus 40, which is 2 times 243 plus 40. How do we write 40 as a sum of powers of 3? Well, 40 is 27 plus 13, and 13, again, you just have to do a little bit of arithmetic. That's 27 plus 9 plus 3 plus 1. So this is 2 times 243 plus 27 plus 9 plus 3 plus 1. So the answer to this problem is 526 is 2 times, what is 243? 1, 2, 3, 4, 5. It's 3 to the 5th power plus 3 cubed plus 3 squared plus 3 to the 1st power plus 1, which is 3 to the 0. So this is the three-adic representation of 526. And there are several more problems like this, and these are nice problems because in number theory, you're supposed to learn and hopefully enjoy playing with numbers. Number theory is about numbers, and the simplest numbers in some sense, which are the positive integers.
Professor, can you do the number 10 from homework? It's a proof exercise.
Okay. So this is section 1.1, exercise 10. This is a proof. Prove that n cubed minus n is divisible by 6 for every n. Well, maybe the first thing to do is try to convince yourself that this is true. So let's look at some experimental or computational data. Suppose you let n equal 0. So n cubed minus n is 0 cubed minus 0 is 0, which is 6 times 0. So this number is divisible by 6. If n equals 1, n cubed minus n is 1 cubed minus 1 is 1 minus 1, which is also 0, which is 6 times 0. So the statement is true for 1. What about n equal 2? 2 cubed minus 2 is 8 minus 2 is 6, which is 6 times 1. So again, this number is divisible by 6. What about n equal 3? 3 cubed minus 3, 3 cubed is 27. minus 3 is 20. 27 minus 3 is 24, which is 6 times 4. Again, it's divisible by 4. Sorry, again, it's divisible by 6. What about n equal 4? You get 4 cubed minus 4. What is 4 cubed? 64. Minus 4 is 60. That's 6 times 10. Again, it's divisible by 6. What about minus 7? I didn't say the numbers had to be positive. What about a negative number? Minus 7 cubed minus minus 7. What is minus 7 cubed equal to? What is minus 7 cubed?
Negative 343.
Negative 343. And minus minus 7 is plus 7. So this is minus 336, I believe. And minus 336 is 6. If you divide 6 into 336, this goes 56 times. So this is 6 times minus 56. Again, this number is a multiple of 6. So this is just some experimental data, maybe to convince ourselves that the problem really is true. I mean, sometimes you make a mistake, you say prove something, but it turns out to be not true and you can't prove it. So this suggests that the problem is true, and then the question is, how do you prove it?
Professor,
Yes.
Can I ask a question?
Of course.
Yes, so can we say, like, since the n to the third minus n is basically odd, so will be the
Well,
same.
wait. It's not odd. In fact, it's always even. Because if it's divisible by 6, it's divisible by 2. So it's always going to be even.
No, but I mean in the sense, like, if we see it as a function, if we plug negative n, for example, the result will be negative the function, right?
Yeah.
So does that mean that, like, the negative numbers will always be like the positive number, but just with a negative in the front, and that will take care of the negative numbers, like the proof of the negative number? So basically,
Okay.
you can prove the positive, and it will be divisible, but for the
Right.
negative.
Everything you said is correct.
Okay, thank you.
I mean, it's enough to prove it for positive numbers, but we still have to prove it for positive numbers. So let's try and do it. So, so we still have the problem, prove n cubed minus n is divisible by 6. Any suggestions about how we might try to do that?
We can do it by induction.
By what?
Induction,
Okay.
since we already proved the base cases.
So let's say try a proof by induction. So suppose it's true for some number n, which means n cubed minus n is 6 times some number d, right? This is what we start with. And we must prove the statement for n plus 1. So n plus 1 cubed minus n plus 1, right? So this is what you're suggesting we try? Right? If it's true for
Yes.
n, see if it's true for n plus 1. So what do we do with this? Well, we could just expand n plus 1 cubed. So if you take n plus 1 and you cube it, you get n cubed plus 3n squared plus 3n plus 1. And you're subtracting n plus 1. Any questions about what I'm doing? So to prove something by induction, first you prove it's true, let's say for n equal 1. And we know when n equals 1, this number is 0, which is divisible by 6. And then we say, assume it's true for some number n. So assume this is true for n. We want to prove it for n plus 1. That is, we want to prove that n plus 1 cubed minus n plus 1 is divisible by 6. So let's expand this. N plus 1 cubed is this, right? If you don't know this, now you know it. I mean, it's just a matter of multiplying it out, but it's a basic fact. And so this is n cubed plus 3n squared plus 3n minus n is 2n, and 1 minus 1 is 0. So this is equal to n cubed plus 3n squared plus 2n. And we have to show that's divisible by 6. Let's see, what could we do with that? I don't know. Any suggestions?
So we could, so from n to the third minus n equals 60, we could say that n to the third is equal to 60 plus n.
Okay, so this means that n cubed is 6d plus n, and you're saying substitute that in here.
Yes.
So we would get 6d plus n plus 3n squared plus 2n, which is 6d plus 3n squared plus 3n. And then what?
We could factor a 3 from the,
All right, so you could factor out a 3n, you get 3n times n plus 1.
so if we just look at the n and n plus 1, that's basically an even number because it's two consecutive numbers.
Right. So that's very good. So n, if you have two consecutive numbers, one is even, one is odd. So the product is even because it's an even number times an odd number. So this is even. This is divisible by 2. N times n plus 1 is 2k for some k. So this is 6d plus 3 times 2k, which is 6d plus 6k, which is 6 times d plus k. So this is a multiple of 6. So we have to do had to do a little bit of work here, but it's okay. So this is a proof.
There's any easier way to do it?
Well, so, easy or hard is in the, eyes of the beholder. We could try another way, and you can tell me whether you prefer one or the other. Remember, we're starting with n cubed minus n, and we want to prove it's divisible by 6. So at one step in the previous proof we factored. We could also just try to factor this. You can certainly factor out an n, and then you get n squared minus 1. And then one of the factorizations that everyone's supposed to know is that n squared minus 1 is n minus 1 times n plus 1 times an n. So n cubed minus n factors like this. And if you look at this, this is a product of 3 consecutive numbers, n minus 1, n, and n plus 1. Like suppose we had, I don't know, 19 cubed minus 19, when n equals 19. This says this is equal to 18 times 19 times 20. Right? That's just an example of this. And what can you say about 3 consecutive numbers? Well, first of all, any 2 consecutive numbers is even. So one of these numbers is even. This is even. But the other thing you can say about 3 consecutive numbers is one of them is also divisible by 3. So one of these numbers is divisible by 3, and one of them is divisible by 2. That's what even means. And I don't know, we haven't proved it yet. We'll prove it shortly, but if a number is divisible by 2 and by 3, it's divisible by their product. So if you put this together, we get divisible by 2 times 3 or 6.
I'm sorry, Professor, quick question. What is dividable by 3 again?
Sorry?
What is divisible by 3, n plus 1?
If you have 3 consecutive numbers, so if you have so exactly one of 2 consecutive numbers is divisible by 2. Right? Because like you give me a number, 8. 8's divisible by 2. Give me a number like 13. Well, 13 is not divisible by 2, but 14 is. If you take 2 numbers in a row, one is even and one is odd. Right? So if you have any 2 consecutive numbers, one of them is divisible by 2. And similarly, one of 3 consecutive numbers is divisible by 3. I mean, here's like a simple proof of that. Suppose you take n, if you divide it by 3, you get 3 times some quotient r plus a remainder, and r is 0, 1, or 2, right? So if r is 0, n is 3q, which is divisible by 3. If the remainder is 1, n is 3q plus 1. So n plus 2 is 3q plus 1 plus 2, which is 3q plus 3, which is 3 times q plus 1. So if the remainder is 1, n plus 2 is divisible by 3. If the remainder is 2, n is 3q plus 2, so n plus 1 is 3q plus 2 plus 1, which is 3q plus 1, 3q plus 3, which is 3q plus 1. So no matter what number n you pick, either n is divisible by 3, or n plus 1 is divisible by 3, or n plus 2 is divisible by 3. So if you take 3 numbers in a row, and just try it, take any 3 numbers in a row, exactly one of them has to be divisible by 3. So n cubed minus n, if factors like this number is divisible by 3, it's divisible by 2, and therefore it's divisible by 6. Right? Divisible by 3 and divisible by 2 implies divisible by 6.
Okay, thank you.
Okay. Any other questions about what we talked about on Wednesday last week, or about divisibility, or about the homework?
Yeah, the lines in number
Question.
9.
Can we see a bigger version of your screen?
Sorry, what?
Can we see a bigger version of your screen? Because I'm having trouble seeing it in my screen. It appears too small.
Well,
I think
that's,
you can double click it to make it larger.
no,
Eh?
so this is, I'm already filling up my whole screen. So I can't, I mean, so it doesn't get any larger. This is, I mean, it may be on your computer, you can enlarge the image, but this is as large as this screen works. And it should be okay, because I've been doing this now for 3 or 4 semesters, and this is the first time anyone thought that the image was too small.
So I'm seeing everybody's screen.
In any case,
Professor,
I only can do this once. I can make it smaller, but I can't make it any bigger.
Are you sharing your screen?
No, I have a camera facing directly onto the page. This is sharing the
This one.
screen. No, I mean, this is, I'm using a document camera. So I have a, what you're looking at here, this is the base of a camera, which is looking right down on the paper, and it's filling up the whole screen.
Oh,
I can make it smaller. I cannot, yes. Anyway, that's the best we can do.
Professor, can you do the last one for me, number 9?
I'm sorry, I can't understand what you're saying.
Yeah, number 9. The exercise number 9.
So let's move on to section 1.2, which is about the greatest common divisor of a set of 2 or more integers. And just to put this in the proper context, what we're really talking about is an important example of what is called a group in algebra and number theory. So we have to define what is called a group. So if you've taken algebra, you've seen this already, but I don't assume anyone has taken algebra. We start as follows. So let G be a set. So a set is just some collection of objects, and it's non-empty. There's something in it. And by G times G, this is the set of ordered pairs. So an ordered pair is something that looks like X times Y, with X in G and Y in G. And a binary operation on G is a function from G cross G into G. So this sounds perhaps a little bit abstract, but all we're talking about are things you know very well. So for example, if we let G be Z, Z is the set of integers. So addition is a binary operation on Z. Like for any pair, 3, 7, that gets sent to 3 plus 7 or 10. I mean, to every pair of numbers, you can add them. Binary operation. Multiplication is another binary operation. Right? 3 times 7, if you multiply it, you get 3 times 7 or 21. So if you have a set, a binary operation is just you assign something in the set to every pair of elements of the set. Just as with addition, to every pair of numbers, you assign their sum. And with multiplication, to every pair of numbers, you assign the product. So that's all a binary operation is, right? That's all it is. Okay. Now, this set with a binary operation can have some basic properties, and all you have to do is keep in mind addition and multiplication and see that those properties are satisfied. So there's a property called associativity. So the binary operation is associative means, suppose we denote the binary operation by like this star. So if I have two elements, X and Y, you get some element X star Y. That's the binary operation. So if these were like real numbers, this could be addition, or it could be multiplication, it could be many things. And we say that the operation is associative if X times Y times Z is the same as X times Y times Z. So it doesn't matter. Binary operation means you do things two at a time. You can't multiply three things at once. The only way you can multiply three things is by multiplying two of them and then the third. And whether you do it by X times Y and then Z, or Y times Z and then X times Y times Z, the operation is associative if these turn out always to be equal. Just as, for example, 3 plus 9 plus 25 is the same as 3 plus 9 plus 25, because this is 12 plus 25, which is 37, and this is 3 plus 34, which is 37, right? So that's what associativity means, right? And a binary operation may or may not be associative, but we like ones that are. That's what associativity means. Then there's the property of having an identity element. So we say that the binary operation has an identity, an element E in the set G is an identity if when you apply, and when you look at X times E or E times X, they're equal, they're both equal to X. So that's what an identity element is. So for addition, the identity element is the number 0, right? Because for any number like 7, 0 plus 7 and 7 plus 0, they're equal to 7. For multiplication, the identity element is usually denoted by 1. 1 times 7 and 7 times 1 is 7. So for ordinary addition, there exists an identity, the number 0. For ordinary multiplication, there's an identity, which is the number 1. Right? And inverses. So the binary operation has inverses if for every X, there exists a Y such that X times Y and Y times X is equal to the identity. So for example, for addition, the inverse of 7 is minus 7. Because 7 plus minus 7 and minus 7 plus 7 are equal to 0. Okay. For multiplication of real numbers or fractions, the inverse of 7 would be 1/7. 7 times the 7th, or 1/7 times 7, is equal to 1. Okay. So this is just giving a name to what you already know in the most important cases. So what is called a group is a non-empty set G with a binary operation that satisfies these three properties. One, it's associative. Two, the existence of an identity. And three, every element has an inverse. And this concept of a group is one of the most important ideas in mathematics. I'll give it a star because it's so important. What are some examples? Well, Z under addition is a group. Addition's associative, 0 is the identity, and the inverse of n is minus n. Z under multiplication is not a group. Why is it not a group? Multiplication is associative. The integer 1 is an identity, but elements don't have inverses. For example, 7 has no inverse under multiplication in Z, right? There's no integer n such that 7 times n is equal to 1. If you take Q is the rational numbers, which are the fractions. And take Q, I'll call it Q star, which is Q with 0 removed. So this is the non-zero rationals. This is a group. Under multiplication, the inverse of A over B is the fraction B over A, because A over B times B over A is 1. If you include 0 with the rationals, it's no longer a group, because 0 doesn't have an inverse. There's nothing times 0, which is equal to 1. So this is a typical thing in mathematics. It takes 5 minutes or less to write down the definition of a group, but people spend a huge amount of time and need to spend a lot of time to understand this concept. So this requires a fair amount of thinking, I believe. What's another example of a group? Well, suppose you take 2 by 2 matrices. So that's something that looks like A, B, C, D. So if you've never seen a matrix before, You don't have to pay attention to this, but there's a way to multiply matrices, right? So this is 2 by 2 matrices, and the determinant, let's call this A, this matrix. The determinant of A, DET of A, is defined to be AD minus BC. And if you let G be all the 2 by 2 matrices, so A, B, C, and D are real numbers. R means the real numbers. And the determinant AD minus BC isn't 0. This is another example of a group. It's a multiplicative group under matrix multiplication. Now, some groups have an additional property. A group G is called commutative or abelian. These two words mean the same thing. If the order in which you multiply doesn't matter. If x times y equals y times x for all x and y in the group. So for example, addition in Z is abelian. X plus y equals y plus x. Multiplication in, let's say, the non-zero rationals is abelian. X times y is y times x, right? Like 7 plus 3 equals 3 plus 7. 7 times 3 equals 3 times 7. So ordinary addition and multiplication are abelian binary operations. And again, if you know a little bit about matrices, matrix multiplication is not abelian. Okay. Any questions about this?
So why we classify operations based on group? What is the importance?
Of the concept of a group?
Yes, because we
It's
we
because
do operations.
it unifies a lot of mathematics. So very often in mathematics, things come up and you look at them and you say, and you see they satisfy the definition of a group. And you can prove a lot of theorems about groups. So so if something is true about all groups, it's true for any particular group you find. And you have like a toolkit that's immediately available to you for every group that you find. So instead of having to prove the same theorem 20 times in 20 different courses, you prove a theorem about groups, and then in the 20 times you see a group, you know the theorem's already true. So it's a unifying concept. It's something which occurs in nature. It's like, yeah, they just come up everywhere, and it sometimes and often gives you a lot of information about it, something you're studying, if you know it's a group. That's all. I mean, and we'll see some examples of that very quickly. But it is really a very fundamental fact, and it matters no matter what subject you're studying. I mean, applied mathematics and differential equations and statistics, you find a lot of groups. And the more you know about groups in general, the more you know about all these different areas of mathematics. So here's an example of a group. The integers under addition with the identity element 0, right? The number 0. Suppose we let H be the set of even integers. So that's 0 plus or minus 2 plus or minus 4 plus or minus 6 and so forth. So H is a subset of Z, right? This means subset. Every element in here is in here. Every even integer is an integer, right? And the set H has the following properties. First of all, 0 is in H. And if X is in H and Y is in H, then X plus or minus Y is in H. All this says is that the sum of two even numbers is even and the difference of two even numbers is even. H all by itself is a group because addition of all integers is associative. So addition of even integers is associative. H contains the identity element 0, and it contains the inverse of each of its elements. If n is even, minus n also is even. So we have the set Z of integers. We have the set H of even integers. Z is a group and H is a group. And we say that so this is an example of what is called a subgroup. A subset H of a group G is a subgroup of G. This is what we're defining. If H is also a group, all by itself, with the same binary operation as in G. So the even integers form a subgroup of the integers. Suppose we let Q star be the non-zero rational numbers, that Q star greater than 0 be the strictly positive
Would it be possible to raise the paper? Thank you.
rational numbers. So the positive rationals, that set is a subgroup of the set of all non-zero rationals, right? Because we know that the rational numbers form a group under multiplication. We know that 1 is a positive number, so 1 is in this set of positive rationals. We know the product of two positive numbers is positive. We know the inverse, the reciprocal of a positive number is positive. So if you look at just the positive rationals, that's a subgroup of the set of positive and negative rationals. So this is an example of a multiplicative subgroup. Here's a slightly more general example than the even numbers. So let D be an integer. That by this notation, D times Z, this is the set of all multiples of D. That's 0, D, 2D, 3D, 4D, and so on forever, and plus or minus. So for example, 5Z is that set consisting of all multiples of 5. 0, 5, 10, 15, 20, 25, and so forth. And minus 5, minus 10, minus 15, and so on, right? So this is a set of all multiples of 5. And we can notice, first of all, that 0 is D times 0 is always in this set DZ. And if you take two elements of the set, D times A and D times B, if you add it, you get D times A plus B. And dA minus dB is D times A minus B. So the set of DZ, it contains 0. It's closed under addition and subtraction. This is always a subgroup of Z. So just as the set of even integers is a subgroup of Z, the set of all multiples of 5 is a subgroup of Z, and for any number D, the set of all multiples of D is a subgroup of Z. Even D equals 0. What is 0 times Z? This is the set of all multiples of 0. That's just the number 0. So 0 all by itself is a subgroup of Z. I mean, it's closed under addition. 0 plus 0, 0 minus 0, there's 0. So this is a very simple subgroup. Okay. Any questions about this? So we'll take a 60-second break, just because I want you to have a chance to look at these definitions and think about them for a minute. All right, so let's prove a theorem. So this is theorem 1.3 in the text. So we're looking at the integers under addition. We have the group Z of integers with the binary operation of addition. Let H be a subgroup of Z. So H is a subset of Z that contains 0 and is closed under addition and subtraction. And the theorem says the following: there exists, so there's an existence part of this, a unique non-negative, that means 0 or positive, D such that H is DZ, is the set of all multiples of D. So it's a general question one can ask, given a group, what are the subgroups of the group? What are the subsets of the group that are also groups? And here's an answer to that question in the case of the integers. We saw that if you take any integer D, the set of multiples of D is a subgroup. And the theorem says that, in fact, those are the only subgroups. Right? Every subgroup is a set of multiples, that is 0 plus or minus D plus or minus 2D plus or minus 3D and so on forever. These are the only subgroups there are. Okay, so that's what we want to prove. So let's prove it. Proof. So we know that 0 is in H, because that's part of the definition of a subgroup. A subgroup must contain the identity element. Now, it's possible that if H is equal to just 0, then H is the set of all multiples of 0. That is, let D equal 0, and we're done. So if H only consists of the number 0, the set of all multiples of 0 is just 0, and we're done. So this is the first case, and that's kind of easy. So we're done. But that's kind of the trivial case. Let's look at the non-trivial case. Suppose FH is not just 0. Right? In that case, then there exists an element A in H with A not equal to 0. Now, A could be positive or negative, but if A is in H, then minus A is also in H, because H is a group. It contains the negative of each of its elements. So if A is in H, minus A in H is in H. If A is negative, minus A is positive. So there's a non-zero element A such that both A and minus A are in H, and this implies H contains positive elements. All right. There exist elements in H which are strictly greater than 0. So now we apply the minimum principle. The minimum principle says that every non-empty set of positive integers contains the smallest element. So the set of positive integers in H is non-empty, right? If H contains a non-zero integer, it contains a positive integer. By the minimum principle, H contains a smallest positive integer, I'll call it D. So D is the smallest integer positive in the subgroup H. So H is closed under addition, which means 2D, which is D plus D, is also in H. But then 3D, which is 2D plus D, is in H. And 4D, which is 3D plus D, is in H. And in general, if ND is in H, then N plus 1D, which is ND plus D, is in H. So by induction, H contains ND for all positive integers N. But because H is a group, it contains the negatives of everything. So H contains also minus ND for all positive integers N, which means H contains all multiples of D. That is, the set of all multiples of D is a subset of H. And I want to show that, in fact, H is exactly the set of all multiples of D. There's nothing else. All right. In other words, we have to prove that if A is in H, then A is equal to D times Q for some integer Q. That is, every element of H is a multiple of D. How do we do that? Well, we apply the division algorithm. So let A be an element of H. Divide A by D. This is the division algorithm. We have A is D times Q plus R, with R, the remainder between 0 and D minus 1. So what do we know? We know A is in H and D is in H. which means DQ is an H. And H is closed under subtraction. So A minus DQ is also an H. But A minus DQ is equal to R. So what do we have? We have R is an H, and R is between 0 and D minus 1. But D is the smallest positive integer in H. That's how we chose D. We applied the minimum principle to find the smallest positive number in H. And R is also in H, and R is between 0 and D minus 1. But R is smaller than D, and D is the smallest positive integer in H, so R cannot be positive. So R in H and 0 less than or equal to R less than or equal to D minus 1 implies R has to be 0. If R were positive, it would be a smaller element of in H than D. And if R is 0, A is DQ. It's a multiple of D. And we're done. We're done with at least with half of the theorem that says that. So therefore, H is equal to DQ for some D greater than or equal to 0. If H is just 0, then D is 0. If H is not just 0, D is positive.
Professor,
Yes.
sorry, just to ask a quick question. So you would know that it wouldn't be a negative, say like, so R couldn't be like a -1 or a -2 because that would just be negative D. Is that?
No,
Is that
no, no.
right?
R can't be negative because the division algorithm says if you divide A by D, you get a remainder which is between 0
In
and D minus
between.
1.
Okay, and then therefore it has to be 0. I understand.
Right.
Thank you.
Sure. So this is half of the theorem. This is the existence. We need to prove uniqueness. So we want to show D is unique. And what does that mean? It means suppose we have D and D prime positive integers, and H is equal to DQ, but it's also equal to D prime Q. We must show D is equal to D prime. That is, if H is the set of all multiples of D, D positive, and if H is also the set of all multiples of D prime and D prime is positive, then D equals D prime. So let's see. We know that D prime, well, that's D prime times 1. Sorry. If H equals DZ and D prime Z. So D prime is D prime times 1. So that's an element of D prime Z, which is the same as the set DZ, which means D prime is a multiple of D. So D prime equals DQ for some integer Q. And similarly, D, which is D times 1, is in the set DZ, which is D prime Z. So that says D is a multiple of D prime. So D is some D prime times Q prime for some integer Q prime. So if I put these two together, I get D is d prime q prime, but d prime is dq times q prime. This is d times q prime. D equals d times q prime. Divide by d, you get 1 is q prime. So the only way a product of integers is 1 is if q equals q prime is plus or minus 1. But d and d prime are positive, so q is positive. So q and q prime are 1. So d prime equals d. And that's our uniqueness statement. So again, everything I'm doing is in the book, and I posted this chapter 1 already on Blackboard. So if you don't have the book, you certainly have the chapter to study. There's no reason not to be studying it. And that's the proof of the theorem. So this is really a very important theorem in number theory. And the more time you can spend understanding the definition of a group and the proof of this theorem, the better you will understand number theory. It really is very important. So in elementary school, you probably learned about common divisors. Of integers. For example, if you let a equal 6 and b equal 15, if you take the number d equal 3, this divides 6, and 3 divides 15. So we say 3 is a common divisor of 6 and 15. And in fact, it's the largest common divisor of 6 and 15. Of course, 1 also is a common divisor, right? I mean, to say that 3 divides 6, that just was 6 is 3 times 2. 3 divides 15, 15 is 3 times 5. So we see that this 3 is a common divisor. Of course, you could also say that 6 is 1 times 6. And 15 is 1 times 15. So 1 is also a common divisor. So these are 2 positive common divisors. The largest happens to be 3. If we take, for example, a equal to 30 and b equal to 42, what are the positive common divisors of a and b? Right? What are the numbers that divide, that are positive integers that divide both 30 and 42? Can someone give me some of them?
2.
2. Anything else?
3,
3. Anything else?
6.
6. Anything else?
1,
1. Anything else?
5.
Well, 5 doesn't divide 42.
Oh,
Anything else? No, then there's not. So these are all the positive divisors, and the greatest common divisor of 30 and 42 is 6. That's just the largest number. It's the greatest number in the set of common divisors. In fact, we can actually do a little bit of arithmetic, I think. I take 7a and 5b and subtract. What is that? That's 7 times 30 and 5 times 42. No. Let me do it differently. Let me make it 3 times a minus 2 times b. That's 3 times 30 minus 2 times 42. 3 times 30 is 90, and 2 times 42 is 84, and the difference is 6. So the greatest common divisor of 30 and 42 is 6. And I could actually write 6 as this sort of linear combination of 30 and 42. 3 times 30 minus 2 times 42 is equal to 6. So this is a special case of the following theorem. This is the last thing that I'm going to do this morning. So this is theorem 1.4. Says that A be a non-empty set of integers, not all 0, then A has a unique greatest common divisor. So I was just looking at the greatest common divisor of 2 numbers, but we can define the greatest common divisor of any set of integers. It's just the largest positive integer. It's the largest integer that divides all of them. And of course, every set of integers has a common divisor because 1 divides everything. And there may or may not be a common divisor bigger than 1. But this says that every set of integers, non-empty set of integers, has a unique greatest common divisor, and there exist integers a1 up to a sub k in the set A, and integers x1 up to x sub k, such that the greatest common divisor of A GCD stands for greatest common divisor, is this linear combination A1x1 plus A2x2 up to A sub k x sub k. So this says that the greatest common divisor of a set of integers is a linear combination of integers in the set. And we just saw an example of that. Suppose we let A be equal to the set of numbers 30 and 42. Then the GCD of A, the largest, the greatest common divisor is 6. And we saw that we can write 6 as 30 times 3 plus 42 times minus 2. So this is my A1 and this is my X1. This is A2, this is X2, right? So the example we just computed is an instance of this theorem. Okay. So the proof uses the theorem we just proved in a very clever way. So the proof says the following, that H be the set of integers, the subset of Z, consisting of all integers of the form A1x1 plus A2x2 up to A sub k x sub k, where A1 up to AK, K can be anything, are in H, and X1 up to X sub K are in Z. So these are all sort of integral linear combinations. That's just the language we use of A1 up to A sub K. And I claim H is a subgroup of Z. Well, first of all, for any A in H, 0 is 0 times A is in H. So H contains 0. And if you have A1 X1 up to A sub K X sub K in H, and A1 prime X1 prime up to A sub K prime X sub K prime in H, you have two linear combinations. If you add them, you get A1 X1 up to AK XK plus A1 prime X1 prime up to AK prime XK prime. This is
The
also,
paper is a bit low.
sorry?
Okay. Never mind.
So if you just take two linear combinations, you're in H. Right? And similarly, if you subtract. So H is a subgroup. It's closed under addition and subtraction. It contains 0 and it's a subgroup. So by the theorem we just proved, H is dz for some d greater than or equal to 0. And D isn't equal to 0. If D were 0, H would be 0. And we took H to be a set that wasn't just 0. So in fact, we can say for some positive integer D. So this means that every integer in H is a multiple of D. So that means D is a common multiple of H. Sorry, common multiple is a common divisor. Every integer in H is a multiple of D. So D is a common divisor of H. Every element in H is divisible by D. So this number D that generates the subgroup H is a common divisor of H. And I want to show it's the greatest common divisor. Now, of course, if D is in H, then D is A1x1 plus A2x2 up to A sub k x sub k. So it can be written in this form where the A sub i's are in H and the x sub i's are integers. So my common divisor is of this form. That D prime be any common divisor of A1 up to A sub k. That means you can write every one of these AIs, like A1 is going to be D prime times Q prime. Or, you're right. So A prime, A1 is D prime times Q1. And A2 is D prime times Q2 and so forth. AK is D prime times QK. And if I plug these numbers into this equation, I get D is A1, that's D prime Q1 times X1, plus A2, D prime Q2 times X2, all the way up to AK, which is D prime QK times XK. This is D prime. I can factor out a D prime, Q1X1 plus Q2X2 up to QKXK. So D is represented in this way. So D prime divides D. So D is a common divisor. Every common divisor divides D. So D is the greatest common divisor of all the elements in this set H, which means the greatest common divisor of all of the A's. And that's the proof. Let me go through this proof again, because here's the statement of the theorem. A is a non-empty set of integers, not all 0. Show that A has a unique greatest common divisor, and there exist integers so that that greatest common divisor is this integral linear combination of elements of A. And we do that by constructing a certain subgroup of Z, we call it H, consisting of all linear combinations of a finite number of elements in the set A. So for any finite set of elements in A, look at all integral linear combinations. The collection of all these things is the set H. This contains 0, it's closed under addition and subtraction. So this set H is a subgroup. And by the theorem, every subgroup of the integers is all multiples of a fixed number D. So this number D divides every element of H. H contains A. So D is a common divisor of H and A. So this number D, it's in H, so it is a linear combination, A1 up to AK, of elements of A. If you take any number that divides all the A's, it divides each of these numbers, it divides their sum, so it divides D. So D is not only a common divisor, but it's divisible by every common divisor. So it's the greatest common divisor. And that is theorem 1.4. We say that integers A1 up to AK are relatively prime if the greatest common divisor is 1. So for example, 6 and 17 are relatively prime because the largest number that divides 6 and 17 is 1. And it follows from what we just proved that the GCD of a set A is 1 if and only if, or let's say the set of these K integers, some linear combination of them is equal to 1. So for example, if I look at 6 and 17, 6 times 3 plus 17 times minus 1, this is a linear combination of 6 and 17. This is 18 minus 17, or 1. Okay. All right, so what we covered is really less than really 3.5 pages in the book, but there is a lot to think about, and there's a lot of material here to understand. So the more time you spend studying this and trying to understand the proofs, the better. That's a good investment of time. I will probably set up 1 or 2 office hours tomorrow when I'm just online, if you have any questions about number theory to ask. I'm going to have odd times for office hours because people are taking classes at different times and work at different times and so forth. So if I had an office hour every day at 2, there always will be, a lot of people who are just busy at 2. So tomorrow I'll probably set up 1 time in the morning and 1 time in the afternoon. Then it's completely optional. Anyone who shows up, shows up. Just like an office hour on campus. Okay. Any questions before we end for the morning?
Professor, I have a question.
Yeah, go ahead.
I think it was Thursday that you had a problem session.
Areas will be-
I saw that you posted on Blackboard, but for some reason I didn't receive an email, so I didn't notice it, about the session. So when you decide the times for tomorrow office hours, will you send an email also besides the Blackboard announcement?
Yeah, okay. So from now on, whenever I have a office hour problem session, I will post it
Okay.
on Blackboard and I will also send an email to everyone in the class.
Thank you, Professor.
Okay.
Appreciate it.
Okay, that's a very good idea. Thank you.
Professor, I also have a question. So these are being recorded, these classes,
Correct.
and they will be posted on YouTube,
Yes.
but they haven't been posted. None has been posted yet, right?
I believe that I posted last Wednesday's lecture on YouTube already.
Oh, I don't think I have the link to that one.
So on YouTube, there's a channel called Nathanson Math Lectures. And then for each of my classes, there's a playlist. So
Oh.
there's a playlist for Math 316, 616, whatever the class is, 316, 613. But I'll double check. When I post today's lecture, I'll make sure that lecture 1 is also posted.
Sure. Does anybody in the group have the link to anybody in the group?
There's no link.
Yeah, I'm about to send it.
Sure. Thank you. Thanks.
Yeah, you just go to YouTube. Okay. See you Wednesday morning.